All right, so in the last video, we went through an extended example um, showing all the behind the scenes details for confidence intervals for P. And now I'm going to just say it all in a kind of direct way that you can maybe remember and follow this formal procedure. Okay, so how do you define a confidence interval for population proportion P? All right, so confidence interval for P begins by choosing the confidence level, which we write as 1 minus alpha. So it's the number that's less than 1. If we want 95% confidence, we would choose alpha equals 0.05, which would mean 1 minus alpha would be 0.95. For, let's say we wanted 90% confidence level, we would choose alpha equals 0.1, which would mean 1 minus alpha is 0.9. Okay. Next, we calculate the critical Z value. And what is that? The critical Z value is the Z value for a standard normal distribution. It's the Z value here, which leaves us an area of alpha divided by 2 in that tail. Why alpha divided by 2? Because the other half is in the left tail. The other half of the area is in this tail. And this number is going to be negative Z alpha over 2. And then that means that the area in the middle is alpha. No, 1 minus alpha. This area is going to be 1 minus alpha. So how do we calculate Z alpha over 2? The best thing to do is to use Excel. So it's a standard normal, so we use norm.s.inverse. And I want to give it the area to the left, right, which is all of this area, all of that. I don't want to ruin my picture. So all of that area to the left, remember I'm trying to compute this Z value. So I want to do 1 minus the right tail. 1 minus the right tail will give me all the left area. So that's my critical Z value. And if you use, and you can memorize some of these, right? Like if we use alpha is 5%, then you're going to get the critical Z value is going to be 1.96. That's one that maybe you'll just remember, for example. But I don't think I've memorized any other ones. Maybe for a few minutes I might remember it. Okay, now what? So for a non-standard normal variable with parameters mu and sigma, we know that, sorry, we know for a non-standard normal variable, we know that that x lies between what and what with probability 1 minus alpha. So what I'm saying here is if we take what we learned about Z and do the same thing, so I want to have this area in the middle be 1 minus alpha. What do I have to use for the limits now? Well, what I can do is I use this same Z value. It's that, okay, I need more space here. It's that, sorry, let me let me say this a little more clearly. The mean is in the middle. Sigma is the distance here. And so if I go mu minus that many Z, that many sigmas below, that's the left side. And if I go from u up by that many sigmas, 1.96 times sigma, then that's the upper limit. So x will lie between these two limits with probability 1 minus alpha. And that's because, think of this z. Z is the number of sigmas. That's what z means. It's the number of sigmas away from the mean. Okay, so that's true in general for any non-normal variable, for any non-standard normal variable. And in particular, we know that p hat follows a normal distribution with certain parameters that I won't belabor here. I'll just say that the mean value of p hat is p. The sigma for p hat is square root of pq over n, which is approximately equal to the standard error, which is defined to be the same expression with the hat values instead of the population values. And that's true as long as what? As long as n times p is greater than or equal to 5, which we actually are going to check that we don't know p, right? We're going to check that n times p hat is greater than or equal to 5, and n times q is greater than or equal to 5. And realistically, again, we're going to check that n times q hat is greater than or equal to 5. Okay, so step 4. So that's the sigma. So if we go, I'm going to connect this this statement with this stuff, and what that means is, so the unknown p lies within a margin of error E of the center with probability 1 minus alpha, where, you know, I think I need to insert one step here. So step 3.5, it's going to be almost the same. The value p hat lies within the range, the interval from, why am I doing this? Because I want to more directly copy this line. So p hat is like the x. P hat is like the x. So it lies between the mean value plus the critical z value times the standard error, and above the lower limit, which is p minus that. And this expression is called the margin of error E. So now we're ready for that next step. So the unknown p lies likewise within the distance E of p hat. P lies within the distance E of p hat with the same probability, where E is this thing. I know I said I was just going to tell you what it is, but I can't help myself. I need to keep explaining it over and over. Okay, so that's the margin of error. So i.e. P why did I give myself so much space here? Maybe I was going to write this down here. Anyway, that's okay. So finally, I guess what I'm saying is P lies within a margin of error of P hat. So P is between P hat plus E and P hat minus E. And that was because we knew that from up here, we knew that P minus E was, let me just write it first. these lines look almost the same. And remember, I said in the last video, it's like this. If I know that, if I say, you're standing within 10 meters of me, say this is me at the center, and I say, okay, who is standing within 10 meters of me? And you are standing within 10 meters of me. That's the same thing as saying that if I draw the circle around you, well, I'm standing within 10 meters of you, right? I'm in your circle. You're in my circle, I'm in your circle. That's what this is saying. So P hat is in the circle, P is in the circle around P hat, just like P hat is in the circle around P. So that's why these statements are the same. This one is more useful. The second one is more useful, the first one is more useful for us. So, final answer. The confidence interval for P at confidence level 1 minus alpha is this. P less than or equal to P hat plus E, which is, and then on the left-hand side, okay, and that's the grand conclusion. Let's put a box around that. So we can calculate everything on this side is all known from the sample, data, right? All of those things can be computed just from the sample data. The Z value is computed using Excel, and same thing here. This is all known from the sample data. It's the same numbers. So using just the sample data, we can trap the unknown p-value in between. This unknown p is trapped in between. I'll say squeezed, or it's not trapped is a good word. With probability 1 minus alpha. It might not be in that interval, right? But it probably is, depending on what 1 minus alpha is. Okay, so the correct interpretation of this, how do we say this properly? Now, it's very easy to misinterpret this. So I'm going to tell you a good way and then a couple of bad ways. So the correct interpretation, and let's assume that we're using a 5% alpha. The correct interpretation is this. For 95% of all possible samples of size n, they all have to be the same size. For 95% of all samples of size n, if we follow, I missed a word here. If we generate the interval, following the above procedure, so if we generate that interval here using the above procedure for the value of p hat for that sample, then p will fall into that interval. So for 95% of all samples, the p will fall into that interval. Okay, so what we say is that we are 95% confident that p lies in the interval of p hat minus p up to p hat plus e. Now, the key thing to know here is that for each different sample, let's say these are different samples here. So this is the first sample, this is the second sample, and then there's there's 20 here, the 20th sample. Each of these has 50. So each of these samples involves 50 people, right? 50 independently selected people. Or I guess I'm thinking of the example we already did. It involves n people. for every sample, we would get a different confidence interval, right? These are all different. This interval here changes depending on p hat, and so we're saying that, whereas the true value never changes. The true value is just what it is. But what we're saying is that for 95% of all these different samples, all the different confidence intervals, 95% of them contain the truth. One of them, in this case, this one, does not contain the truth. So just 1 out of the 20 or 5% of these don't contain P, the true value. So now this is not the same thing as saying, our book does a good job with saying this, it's not the same thing as saying that the probability that P lies in the interval P hat minus E, P hat plus E is 1 minus alpha. It's not that. That's wrong. Why is that wrong? It's not that. Why can't I say that? It's not the probability, not the same thing saying the probability that P lies in the interval is 1 minus alpha. Because P is not a random variable. P is not random. There's no probability that P is this or that. P is just what it is. It doesn't change. Because, so P is not random. What is random is P hat. The interval is random. The confidence interval is what's random. It depends on the outcome. For 95% of those intervals, they'll contain the truth. So the way, in words, we call that confidence. We're 95% confident that P lies in the interval. We have to use a different word to show that we're not implying that P is random. Okay, tricky, right? Now, what we're going to do is a couple more examples in, actually no, we're going to do one example here, and then I'll leave the rest for the next video. So this is going to be a kind of typical example of doing a confidence interval, and I'm just going to try not to drag us into the details. I'm just going to go straight through, get the interval, and be done. Okay. So this is from the textbook. In exercise 13 to 16, so that's what we're doing, use the given sample data and confidence level, that means alpha. In each case, A, find the best point estimate. So the best point estimate. And then we're going to find B, the margin of error. E. And then we're going to write the confidence interval. Conf interval. And then D, we're going to interpret it. Okay, so what are we talking about? This drug, Eliquis, apixaban, whatever. These are weird words for drugs, right? Commercial drugs. So this drug is used to help prevent blood clots in certain patients. In clinical trials, among 5,924 patients, that's going to be the N, among that many patients treated with Eliquis, 153, that's the X, developed the adverse reaction of nausea. Construct a 99% confidence interval for the proportion of adverse reactions. So we're going to say that, so I'm going to rewrite this stuff in a second. So let's define a couple things. So let's define P is the proportion of people who experience adverse reactions in the whole population. This is for the whole entire population. We don't know P. P hat is the sample proportion, which in this case, the proportion in the sample who had adverse reactions, 153 over 59. Let me specify this is x over n. 153 over 5924, which is 0.02582. Um, 27. We'll round it later if we have to. And so, okay, about 2.5% experience adverse reactions. And while we're at it here, let's calculate Q, right? Q hat is 1 minus P hat, which is 0.97417. Okay, now what is our best point estimate? Our point estimate of P is just P hat, which is 0.02587,827. Done. That's part A. Part B, identify the value of the margin of error. So the margin of error is called E, and we calculate it with the critical Z value times the standard error of P hat, which is critical Z value times square root of P hat Q hat over N. Now what is the critical Z value? So if alpha is 0.01, which makes 1 minus alpha is 0.99, that's what we want. Oops, because it says 99%. Then what is the Z score? Z of 0.01 divided by 2 is norm dot S dot inverse of 1 minus 0.01 divided by 2, which is what? It should be more than 1.96. 1 minus 0.01 divided by 2. 2.5758. 2.5758. That's generally true. If you want more confidence, 99%, you have to use a wider confidence, a wider margin of error. So what do we get? We get E is 2.5758 times square root of 0.0258. I'll start rounding things off here. 9742 divided by, what was N? N is 5,924. So that's the margin of error times 0.02583 divided by 5924 square root times 2.578. 2.5758. And what do I get? A pretty small number, 0.005308. Okay, now what? That's the margin of error. Now, at some point in here, we need to check the requirements, right? We need to check that n times p hat should be at least 5. And what do we have here? N times, if you think about it, n times p hat is actually the same as x, which is 153. That's more than 5. N times q hat is going to be, again, it's the number of failures. So it'll be, let me show you the long way first. So it's p times 5924's n times 1 minus p hat, which is 5924 minus actually let me leave that as n. It'll be clearer if I leave that as n. So it's n minus n p hat. So what I get is n minus x. So that's the number of failures. The number of failures is 5924. So basically what the requirement is saying is as long as you have at least 5 successes and 5 failures, then you're fine. I find that easier to remember. If you have as long as you have at least 5 successes and 5 failures, then you can proceed. And here we certainly do. Okay, so that's the margin of error. And part C, construct the confidence interval. So the 99% confidence interval for the population proportion P is P hat minus E less than or equal to P hat plus E. So what did we have? We had, what was P hat? P hat was 0258. I'll just keep those as 4 decimal points. 0258 minus E, 0.0053. It's better to round off at the end, so let me actually add another digit here. 025827. And then on the other side, it's 025827. 025827 plus that number. Okay, and what do I get? What do I get? I get P is less than 0.0311 and greater than same numbers but subtracting 0.0205. So that's it. We've got 3. We'll leave it rounded to 3 since they're it would be reasonable to round it to 3 digits like this in this case. Okay, so that is our 99% confidence interval. Now, what's the final step? Write a statement that correctly interprets it. The interpretation is if we follow the above procedure, so let's write it, let's see, we are 95% confident that P lies in the interval from 0.0205 to 0.0311. So that's an adequate answer. And a slightly more involved answer would be that for 95% of all samples, P would lie in the interval resulting from the above procedure, in the interval produced by the above procedure. It'll be a different interval each time, but if we follow the same procedure, 95% of the time, it will capture the truth. Okay. So that's the end of seeing examples for confidence intervals for P. Next video, we're going to think about the reverse process, which fortunately is sort of a shorter thing. what if we know the margin of error that we want or need? How do we figure out the n to use? All right, so I'll see you then.